G'day, in this video we're going to be looking more closely at nuclear reactions that occur in stars. This video covers content in dot points 8.1.3 and 7. This inquiry question looks at the evidence that we have for the origins of the elements which are effectively made in stars through nuclear processes. Dot point 3 asks us to apply Einstein's concept of the equivalence between mass and energy and relate it to the processes that occur in stars. And dot point 7 very specifically outlines that we need to have a look at two very common processes in stars, the proton-proton chain and the CNO cycle. At this stage, we've done a fair amount of practice in videos looking at applying mass defect quantitatively. So we're not going to do that again today, but we are going to use the concepts of binding energy and mass defect to justify how and why stars undertake nuclear processes. And from there, again, we'll look at the proton-proton chain and the CNO cycle as examples of these processes. In previous lessons, we have looked at this diagram quite extensively, and we've talked about the idea that in nuclear processes, generally speaking, we have nuclei either combining or breaking apart through fusion and fission in order to make products which have a higher binding energy per nucleon. Effectively, these daughter nuclei are more stable than the parent nuclei. When we start to think about stars, they are predominantly composed of light elements. Materials such as hydrogen and helium were the first elements produced, and they are remnants of the Big Bang. These stars then provide conditions through which they can fuse and start to form heavier and heavier elements, again with more stable nuclei. However, this does have an upper limit. Once we get to about iron, fusion to make heavier elements in stars generally does not occur, and it's quite rare. However, there is an exception to this. This is because the formation of a heavier element would reduce the binding energy per nucleon, and this would require a large input of energy to form these new nuclei. Even though stars are high energy environments, they do not supply enough energy for this to naturally or spontaneously occur. However, this can happen in certain rare circumstances like a supernova. In these conditions, there is enough energy to be supplied to the atoms to bring them together, to fuse them together, and produce products with lower binding energy per nucleon than was initially there in the original elements. Another way of thinking about these fusion concepts is that as we work towards iron on our x-axis through these fusion processes, these processes are exothermic, meaning that they release heat and energy. The reason that they do is due to the mass defect. As we increase the binding energy per nucleon of our nuclei, there needs to be a loss of mass, which is then converted into energy and released into the surroundings. The opposite is true for fusion that runs beyond iron and helps to explain why it doesn't occur naturally in stars. These processes are endothermic. What this means is external energy needs to be absorbed by the particles in order for there to be a transformation of mass and form heavier products with lower binding energy per nucleon. So this then brings us to some of the nuclear reactions which occur in stars, the first of which being the proton-proton chain. Essentially, in this process, we have 4 hydrogen atoms which are combining to form a helium nucleus. But it's not as simple as getting 4 of those hydrogens and smashing them together. There is a little bit of a process that is involved. So let's talk about each of the steps. Note too that in the diagram, you're going to see the production of particles like this. The Greek letter nu here, Nu, is what we call a neutrino, and the white particles are known as positrons. In a few lessons' time, we're going to be breaking down and introducing these particles, but for the moment, we're going to ignore them. By removing this little bit of complexity, it's going to simplify what's happening in the proton-proton chain and allow us to more easily analyze and understand the basic concepts that underpin this process. So the first step is to take 2 hydrogens and combine them, forming helium. However, helium usually naturally occurs where there are 2 protons and 2 neutrons combined. Here we just have 2 protons. Due to excessive Coulomb repulsion and not enough strong nuclear force to hold them together, quite quickly, almost instantaneously, there is a decay process. So instead of there being 2 protons, one of the protons decays and instead forms a neutron. Essentially, we have deuterium, heavy hydrogen. There's 1 proton and 1 neutron. We can see that there in the diagram. In the second step, we get our deuterium, which is made from 1 proton and 1 neutron, and we add on another hydrogen, and this forms helium. But again, not the regular stable helium with 4 nucleons in it. This one still only has 3. From this point in the proton-proton chain, we don't have an additional hydrogen that simply just adds on. Instead, this process happens twice, and we get the 2 helium-3 products at the end and combine those. When these 2 particles smash together, in total there are 1, 2, 3, 4 protons and 2 neutrons. When they combine, this forms beryllium-6. Beryllium has 4 protons, and beryllium-6 has 2 additional neutrons to make up the mass. For similar reasons as our helium-2, beryllium-6 is extremely unstable as well and almost instantly decays. And its decay process, however, looks a little bit different to the one that we saw up here. Instead of a proton transforming into a neutron, we instead have the nucleus split apart. And as such, we have a product of a helium-4 nucleus, as well as 2 hydrogen-1 nuclei, or simply 2 protons. If we were to condense this process down and simplify it, what we can say is that we have 1, 2, 3, 4, 5, 6 protons, which all combine, but they don't form a nucleus with 6 particles in it. Instead, we form 1 helium-4 nucleus, and there are 2 protons left over at the end. And while these protons participate in the nuclear process, they are not a part of the final product. We can see that being written here that 6 protons form, again, our helium-4 nucleus and our 2 spectator protons. We could simplify this even further and say that all we really need is 4 protons forming a helium nucleus. Now, while this isn't exactly what happens mechanically, this is just a simple summary which outlines all of the necessary reactants and products while ignoring all of the spectator particles. What we know in truth is that there is quite a large involved process which is required to get these 4 protons to become the helium nuclei product at the end. There is another process that we look at in this course too, and it's known as a CNO cycle. And you'll notice that the overall reaction is written exactly the same as the proton-proton chain. Ultimately, we take 4 protons and they form a helium nucleus. However, the mechanisms that we take to get to this product from the same set of reactants is a little bit different. When reading the diagrammatic version of this cycle, we start with carbon-12 and we move our way around, and being a cycle, we end up back with a carbon-12 at the end. It should also be noted, as it was similarly in the previous diagram, the positrons and neutrinos are going to be ignored in this process just for now, until we actually learn about them a little bit more explicitly, and in our later lessons we'll come back and we'll have a look at how these positrons and neutrinos actually apply. So let's start from the beginning. We begin with a carbon-12 nucleus and add on an additional proton. This forms nitrogen-13, but it's an unstable isotope, and so it decays quite readily. And this process is very similar to the first step of the proton-proton chain. One of the protons that was in the nitrogen decays to become a neutron. And as such, we end up with a carbon-13 product. This carbon-13 has another hydrogen which is added onto it, making nitrogen-14. Now, this version of nitrogen is very stable, and so it doesn't go through a decay process. Instead, it picks up another hydrogen, forming oxygen-15, which again is an unstable isotope, and similar to the previous examples, one of our protons decays into a neutron, meaning that we end up with the same mass number at the end, but one less proton. And so we form nitrogen-15. This nitrogen-15 picks up the 4th hydrogen, and in this process, the large nucleus with 16 particles and 8 protons splits into 2, forming carbon-12, the material that we had at the start, and our new helium particle. What this means is that the carbon-12 can begin the cycle again, and with a new set of 4 protons, form a new helium nucleus. Now, from this process, there are also other products that aren't just our carbon-12 and helium-4. However, this is the most common product and is one of the more basic versions of the CNO cycle, and is the one that we're going to sort of learn about and analyze. But just bear in mind that there are other processes that can happen here too. This is not the only one. And so again, while there are other particles present, namely the 12 nucleons in the carbon-12, There is no net change to this nucleus by the end, and therefore it forms a cycle, in which it can facilitate the combination of 4 protons to make a helium-4 nucleus. Now, both of these processes can occur in stars, but which stars undergo which types of processes is very much dependent on temperature. The higher the temperature, the more frequent you will see the CNO cycle occurring. And for the cooler stars, you'll actually see the proton-proton chain be a little bit more dominant. So why is this the case? Essentially, you need more energy for protons to fuse with heavier elements such as your carbons, your nitrogens, and your oxygens, because each of those nuclei have lots of protons bundled in, and therefore there is more Coulomb repulsion to overcome. So in higher temperature stars, there is an environment where the protons have more energy, and because they have more energy, they are more likely to overcome that Coulomb repulsion when they come into contact with one of those large nuclei. You'll notice too that for both the proton-proton chain and the CNO cycle, the rate of both processes does increase with temperature. However, it has a much more substantial impact on the rate of the CNO cycle rather than the proton-proton chain. In both cases, a temperature increase will lead to a higher likelihood of a collision between 2 particles, resulting in some sort of fusion occurring. However, this temperature change does have a greater impact on the rate of successful collisions in the CNO cycle. While it's not directly in this syllabus, I thought it would also be worth just introducing something called the triple alpha process. This is a process that occurs in heavier stars when a lot of the hydrogen that forms the bulk of the mass inside the star essentially depletes because it's all become helium. So in these situations, there isn't any more hydrogen available for fusion, so instead the helium that's left over fuses. In this process, we see 2 helium nuclei fuse to form beryllium-8. And then a third helium nucleus, the triple alpha process, 3 alpha particles, then come in to fuse and form carbon-12. It should also be noted that an additional 4th helium nucleus can also interact with the carbon, combine, and form oxygen-16. Now that we have a little bit more of an understanding of the mechanical elements of stars and how they work and function, we're now going to start to, in the next video, build on the idea of looking at different types of stars and classifying them and plotting them on something that we call the HR diagram. But until then, have a good one.